In this video, we will continue our exploration of how to use a series like our 1 over 1 minus x equals 1 plus x squared, on and on and on, as a building block to create other power series for other functions. So, if we start with our 1 over 1 minus x, and we differentiate both sides of that equal sign, so that is, we're looking here and we're going to differentiate the left side, and that is going to give us our 1 over 1 minus x quantity squared, and on the other side we'll take the derivative term by term. So the derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x, and then we'll get a 3x squared and a 4x cubed, and on and on and on. And so that then becomes a power series for a new function right here. The question may be, what is the interval of convergence? And if you try graphing that on your calculator, it at least looks like it's going to converge between -1 and 1. But this idea of how our interval of convergence is affected by different things that we do will be something we continue to explore down the road here. So let's think about maybe differentiating term by term. So we have a theorem, and if we have a function and it's equal to some power series, an infinite power series, and we know its interval of convergence, then we can differentiate that series term by term, which will look like that, and that will become the convergent series for the function f prime of x, and we'll have that same interval. Now, notice it's not trying to claim what's going to happen at the endpoints of that interval. That's something that will take a separate study altogether. But at least on the insides of that interval, not worrying about the endpoints, we're going to keep that same interval of convergence. We'll see later we can sometimes lose or gain a point at the very end of the interval when we integrate or differentiate. So here's another idea. We can integrate to find a new series for a new function. So if we integrate this, let me change our colors here. So if we integrate the left side, the integral of 1 over 1 plus x is going to be the logarithm. And if we integrate the series term by term, we're going to get the integral of 1 is x, and then we'll get minus an x squared over 2, then plus an x to the third over 3, and minus x to the fourth over 4, and on and on and on. Okay, and that's another thing we can do. That's going to work as well. So we have a theorem, term by term integration. If we have a function, and it's a power function here, and we know that it converges for some interval, then the series that we get by integrating term by term will equal the integral of that f of x. So we'll get a new series for a new function, and we'll keep that same interval, although we'll have to explore the endpoints because, as we said, that we may gain or lose points just on the endpoint, but the interval itself, the insides, will remain the same for both functions. So clearly we have 1 over 1 plus x diverges at the endpoints, because if you plug in, so we know it's going to converge for the interval from -1 to 1. But if you plug in, the endpoints 1 or -1, you're going to get something that diverges. But so we know that it's going to diverge at the endpoints. And when we integrate both sides, we'll see that we gain a point. It's going to converge at that endpoint x equals 1. So the interval of convergence for that logarithm is going to be -1 to 1, but including the 1 at the end. That's something we're going to look for look at a whole lot more down the road. So let's see how this idea of building a power series for different functions kind of works. So if we want to find a power series for the inverse tangent of x, we remember that the integral of 1 over 1 plus x squared is equal to that inverse tangent, the arctangent. So we're going to build our way up to that. So we know our kind of building block function is that we start with 1 plus x squared, on and on and on, is our 1 over 1 minus x. From that, we know that if we put in negative x's where the x's are, then we get an alternating series because we replace each of those x's by a negative x, and that is going to make all of the odd powers be negative, but the even powers will be positive. Then we can replace the x by an x squared, and so we'll get to 1 over 1 plus x squared, and so we replace now all of the x's by x squareds, and we're going to get to this. This is a skill that we're going to become pretty good at. Then we can finally, now that we've maneuvered it to here, we can integrate both sides to get our series for the inverse tangent. So the integral of our 1 over 1 plus x squared is going to be the inverse tangent of x, and then the integral of 1 is x, and the integral of x squared will be x cubed over 3, and we'll get x to the 5th over 5, and so on. And so this is how we will do this many, many times. And we'll learn some other things as well. So here is an interesting question. Consider a series that has these properties. If we look at a function f of x that's equal to that, let's look at what its derivative is. So the derivative of the left side will be f prime. When we differentiate each term on the series, the derivative of 1 is 0, the derivative of x is 1, the derivative of x squared plus, x squared over 2 factorial is going to be, we'll get a 2x over that 2 factorial, but those will cancel, and so we'll just get an x. When we differentiate the x cubed over the 3 factorial, we'll notice that this 3 factorial is 3 times 2 times 1, and so we'll get, let me come over here, now we've got an x squared over 2 factorial. And if we do one more term, the x to the 4th over 4 factorial is that next term, so when we differentiate that, we're going to get 4x to the 3rd over the 4 factorial, but you can see that will simplify to be x to the 3rd over 3 factorial. When you look at where we are here and compare that to the series we had to start with, you'll see we've got the same thing. So what we're saying then is that f prime of x must be equal to the original function. Think about how many functions you know with that quality. Now consider f of 0. So f of 0 means we're going to go to our, kind of lost my 1 there, we're going to go to our original, and we're going to plug in zeros for all of those x's. Well, that's going to give us 1 plus an infinite number of zeros, and so f of 0 is 1. Okay, can you figure it out? Do you know a function that's equal to its derivative, and that when you plug in 0 for x, you get 1? I don't know if you came up with it, but that's actually going to be e to the x. So it turns out that the power series, the infinite power series for e to the x, centered at 0, is going to be this. Kind of cool. I think I might have one more. Nope. I guess that's it. Oh, there